I love Google Sheets. It's easy to use, free, and powerful. I'm also heavily involved in machine learning and teaching it. So today, I'm going to show you how to implement a linear regression model in Google Sheets. Let's start off by generating two variables. Let's call them x1 and x2. They're going to be random variables, and we're going to generate a bunch of data for each of them. Our function would be something dependent on x1 and x2. And we're going to say that this is a linear combination between x1 and x2. So some constant a multiplied by x1 plus another constant b multiplied by x2 plus c. So this is going to be our y. Let's add a, b, and c here and add some values just to have some examples. This y function is something that we will try to guess or to learn. By doing this, we have to guess a, b, and c. And to spice things up, let's also add some noise to this data, which is a small random variable added to each example. Let's also describe our y value. Y should be a multiplied by x1 plus b multiplied by x2 plus c plus our noise. So we will generate all the y's for that. So we have some inputs, x1, x2, and we have the function y. Now suppose we have a model. Suppose we can make some predictions. How would we know if this model is good or not? How would we compare this predicted model with the correct labels? One of the easiest ways is to compute an error, which is the difference between the correct answer minus the predicted answer. So we will do this for every example. Now, this prediction, this is going to be also a linear model, which is based on three hidden parameters, and these three hidden parameters would basically reflect the mechanics of these A, B, and C. So we will try to find W1, W2, and B to be equal to A, B, and C, our hidden model. Normally we wouldn't know A, B, and C. So we would start with something random here and try to iteratively guess or update these to match whatever the correspondence between x1 and x2 and the y label is. So let's put some guesses here. So we start with W1, W2, and B on some initial values. And let's say that this is the correct model. How would the model work? So it's going to work similarly with what we did generating y. So it's going to be W1 multiplied by x1 plus W2 multiplied by x2 plus the bias. Now we have some errors. Let's also add a chart to have something to monitor. And putting it aside for a moment. We need to update these formulas somehow. We need to make them be auto-adjustable so that at the end of the adjustments, we will have W1 being equal to 10 and W2 being equal to 2 and B equal to 5. So in order to do this, we will use stochastic gradient descent as an optimizer, but stochastic gradient descent depends on iterative update. So that would mean that we need to define the formula for this cell with reference itself. In Google Sheets, in order to enable this, we need to go to File, Settings, Calculations, and by default you'd have this setting set to off. You need to put that on, add a maximum number of iterations here and a threshold, a low threshold here, save settings. So now we have iterative update in Google Sheets. So we allow Google Sheets to solve the formula by iteratively updating the cell if it has a recurrent formula on it until it converges. While we have this error, we also need a single value that would describe the difference between our model and our y. with a single number, and a good candidate for that is mean squared error. And the mean squared error is basically the average over these error terms raised to the power of 2. So we're going to raise this to the power of 2 and get the average of it. So this is the mean squared error. So this is the loss function of our model y hat, and the correct labels y. Coming back to stochastic gradient descent needs to compute a partial derivative of the loss function with respect to each weight. We would update each weight. So let's say y1, it's going to be wy minus an alpha, which is the learning rate, multiplied by the derivative of the loss function with respect to wy. Now let's try to compute it here. So the derivative of mean squared error with respect to w1 is the derivative of mean squared error, which is expanded as the sum of y minus y hat squared over n with respect to wy. And this is 1 over n, and the sum of the derivative with respect to w1 of y minus y hat squared. And this is 2 over n, because we have the second power here, over the sum of y minus y hat multiplied by the derivative with respect to w1 of, and we're going to expand y hat, which is w1 times x1 plus w2 times x2 plus bias. And when you derive this function with respect to w1, this doesn't depend on w1, so it's going to be 0. This is going to be 0. This is going to be 0. This is going to be 1, and you're going to be only left with minus x1. So in the end, you would have the derivative of the mean squared error with respect to w1 be minus 2 over n of the sum of y minus y hat times x1. And conversely, you do the same calculation and find that the derivative of the mean squared error for w2 is minus 2n sum over y minus y hat multiplied by x2, and the derivative with respect to the bias term of mean squared error is going to be minus 2 over n multiplied by y minus y hat. So let's implement them. This is going to be itself, which is J2 minus a learning rate. We're going to put that there. So this is the learning rate. Let's fill out the learning rate. A small learning rate. So learning rate multiplied by minus 2 over n, which is the number of examples. And this is basically the count of how many examples do we have. So count of number of y's multiplied by the sum of products between the error column and the x1 column. Okay, so we need to update this again and moving a bit faster this time. So this is J3 minus learning rate multiplied by minus 2 over the count multiplied by the sum product of the error and the x. This is J4 minus the learning rate multiplied with minus 2 over the count times the sum of the errors. The references were a bit wrong. And now you'd see that this mean squared error, it's supposed to be going down, and these values w1, w2, and b they should be converging to these values, 10, 2, and 5. Also, take a look at this chart where the errors should be slowly going down. So they're slowly converging, and this slowliness comes from the learning rate. We've set a low learning. If we're going to change this to a higher number, then things will progress much faster. Unfortunately, this won't take effect until we stabilize. Okay, so it converged to almost 10, almost 2, and 5. So if we perturb now the weights here and put 12, we're going to see that it's going to converge to the solution 10, 12, and 5. So also maybe some changes to this graph, maybe add another series here just to have something to show, and series apply only to this, and we want to see a trend line and no point size, and also maybe data labels. Let's make this again 2 and see how this is going. So it's going down, 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 down. And this is the mean squared error, 0.5. This is the mean squared error of all the points. And you're seeing the individual points, they slowly converge. So guys, this is it. This is basically a clear implementation of linear regression in Google Sheets. I hope you enjoyed the video. If you want to see more videos like this, you can go to course.ml, where I have more videos and I teach classes for machine learning. Or you can reach me out on Xeting AI, where I'm a co-founder. I hope to see you in the next video and see you soon.